I was racing to finish within 15 minutes, so let me just say a few sort of closing remarks. So this whole figure that I've made here, it has various patterns that are by construction and various patterns that are deep mathematical results. And the way I've set it up is I would say that it's not super easy to see which is which. Uh, so for instance, what about the white zones? The white zones are obviously um, symmetric, and I would claim this is not a deep mathematical fact. That's simply because when I've taken one of these patterns, I've always also printed its transpose. Right? So this means that if I'm in a situation where one of the two diagonal values is non-zero, then the other one will become non-zero using the transpose. So that's why the white zones are matching up. So this in itself is perhaps not so interesting. Uh, Something which is much more striking is that suppose that we look in one of these rows that correspond to a number which is 1 mod 4. Now, I want to emphasize the blue pattern because there's something basic about the blue pattern because that's what I printed last. So of course, this means that whenever I see something blue, I don't necessarily know what's underneath it. But what seems to happen is that whenever I have a blue value in one of these rows, its course, its mirror image is also blue. Right? So this one is this one, this one is this one, so on. So what seems to happen is that if P is a quadratic residue mod Q, and I'm talking about a P which is 1 mod 4, then Q is also a quadratic residue mod P. Right? Because this is the basic information because I printed this at the very top. And then there's something else going on which is also interesting, namely whenever there's a green value in one of these values that has to do with the minus solution, then there's a corresponding brown value in the other parallel and symmetric entry. Right? So again, it's not surprising that I have green and brown next to each other because these are transposes of each other. What is surprising is that this has never been overridden by something red or blue in these situations here. So there's a correspondence between green and brown in the columns and corresponding rows corresponding to 1 mod 4, which again is something non-trivial. Right? So of course, this way of setting things up is perhaps not the cleanest way you could do this. I mean, you would get nicer graphs if you were to order the primes whether or not they were 1 mod or 3 mod 4. But what it shows you is that there's something going on. Right? And then you have to sit down and by ordinary mathematical methods see what's going on. This was originally done by Gauss. It's a very young man, so he invented the term, the golden theorem for it, and was sort of obsessed with it and made many proofs that sort of explains that there's a relation between whether or not Q is a quadratic residue mod P and vice versa, which corresponds to, and there's sort of two different rules. One is for 1 mod 4 and one is for 3 mod 4. And this is explained in the book, but the point is that this setup that I was playing around with these graphs until I found this pattern, and extracting the mathematical insight that comes from that is in the golden theorem is not super obvious from what I have here. But what is obvious that there's something going on, and usually this is what you would expect from a mathematical experiment, that you find some sort of pattern, and the experiment will help you realize that there is one. Then you're going to have to sit down by ordinary methods to work out more precisely what it might be. That would give you some sort of conjecture or hypothesis, and then perhaps you can even prove that. So that's the way these things kind of usually go.